points that I cannot reach, right? The backward points I cannot reach. So what is the property that you get out of this thing? It's not controllability. It's something that is weaker than controllability, right? So this invokes a definition. And this is how mathematicians come with definitions. Because definitions, when you need a definition, it's not just like, here is a definition. So what's the definition? Can you tell me, let's look at these two pictures. So what we're trying to say is that if the Lie bracket covers the entire tangent space, my orbit will cover the manifold. So if my reachable set is the same as the orbit, my system would have been controllable, right? But it's not. So my system, I cannot say that it's controllable. Well, what property does it have? If the orbit covers the entire manifold, my reachable set will look like something like that, right? So they will cover the entire manifold in a biased manner. I can go to some sectors, but not the reverse, okay? So this situation will not happen. We're ruling out this situation. Can you give me a criterion, a mathematical criterion, that differentiates between these two sets? Can you look at them? We're trying to come up with a definition together, right? We're trying to, it's as if we're discovering it now, we're trying to come up with a definition. Can you give me a characterization for this set versus that set? Here is the characterization that they brought. This set has a non-empty interior. Like this point, for example, is an interior point. Obviously, I have infinitely many interior points. When you have an interior point, you have infinitely many. Here, I don't have an interior point. What do you mean? Let's discuss. I mean, if you took real analysis, you're very familiar with this concept. If not, that's okay. Let's discuss it together. So, obviously, the set 0, 1. We live on R. So, this point in the middle, P. P is in the interior of some set E if there exists a neighborhood V around P such that the entire neighborhood is in E. So P belongs to the set 0, 1. Is it an interior point? P is in the interior of 0, 1? Well, from an engineering point of view, of course, yes, right? From the mathematical definition that I just gave you, yeah, because I have here is a neighborhood around P and the entire neighborhood is in the set, okay? Obviously, in this definition, I have that 0 and 1, they are not interior points, right? Why? Because around 0, here is a neighborhood. All these points in the neighborhood, they are not in the set. So 0 and 1, they are not in the interior, okay? So what about, so that's okay, this is very trivial, and what about in R2? Again, let's say this is my E, my set, and here is the point P. Here P was in the middle of the line. Here P was in the middle of that line. Do you think P is in the interior of this rectangle E?
No.
No. Why? Because it's on the boundary, right? Mathematically means what? That if you have any neighborhood around P, now we're in R2, the neighborhood is... Yeah, very good. It's a two-dimensional thing. I have all these points outside. Very good. Any other question about that? Right? Okay. Clear enough? Or you have one more example? You need one more example? Anybody needs one more example? Okay, so very good. So now if I want to really distinguish between these two sets, we're saying what? We're saying in the Lie bracket cover the entire tangent space, you have a good property that is a little bit weaker than controllability, and this property is that your reachable set will look like this. It will not look like this. Okay, so what's this property is that your reachable set will have a non-empty interior. Okay, you will have some point in there, and by the definition of interior, if you have one, you have infinitely many. Because there are some lectures you'll find online, they think non-empty, they mix up non-empty interior with non-empty. So you will find people say, okay, your reachable set will have some points. Of course not, and this will always be satisfied, but reachable set will have some points. Otherwise, we're dealing with very pathological examples. It's non-empty interior, which is actually demanding. Okay? So let's have the definition. Sigma is accessible. So we have sigma control system that is triplets M, F, and U. And we have X naught that is in the manifold. Sigma is accessible. This is the property. From X naught, my sigma is my control system. Accessible, this is the property that we're defining that is weaker than controllability. From X naught, if there exists some time, if you wait a little bit, such that the reachable set from X naught, at most time t, they have non-empty interior. So the interior of this guy is non-empty. Okay. So this is one definition. Then the definition of controllability is what? Sigma is controllable from X naught if there exists some time t such that, let's come up with a definition together. So I have this guy. Now we're saying actually I don't have this issue of directionality. It's as if my orbit coincides with the reachable set. So I will have something like that also. I don't have this issue of directionality and keep collecting things. I will go all the points around in one way or another. So what do you say about that? Well, I have non-empty interior, but not only that, actually X naught is in the interior, right? I can go all points around X naught. So such that X naught is in the interior. This property, we call it more than controllability. Actually, you call it small time locally controllable. Small time locally controllable, and we give it the abbreviation STLC from X naught. We'll see why it's different from controllability in a minute. So this is one definition, this is another definition for small time locally controllable. Here's the difference. If this is your manifold, this is your manifold, this is your X naught, this is your X naught. Now we have learned that for the accessible property, X naught may be on the boundary, and my set looks like that. Here it's like that, the reachable set. Okay? So I can go all points around. Finally, controllable. Sigma is controllable from X naught. This is the definition that we are all aware of. From X naught, if for all X in M there exists some time such that X is in some reachable set. X naught and T, right? With these definitions in mind, so we have just three definitions now. Accessible means what? I have non-empty interior, X naught may be on the bound. STLC, small time locally controllable, I can go all around, X naught is in the middle. Controllable, that I can reach any point eventually, okay? So let's now apply these definitions to the four examples that we created. Today we established reachable sets for 4 examples, right? Here is the first example. This is the reachable set that we're talking about, that in at most time t, which is here equal to this upper plane. Your X naught is the red point. What do you think about this graph? Accessible, very good. This is accessible, so they can cover 2 dimensions. What about small time locally controllable? Not, very good. What about controllable? It's not controllable because I cannot reach negative points in Y. Very good. Let's keep doing that for the 4 examples and we'll be done. Here, it's similar, it's accessible. Look at the reachable set here, how it looks like. It really has non-empty interior, and X naught is in the boundary, the origin. So this is same as before, as 1, as example 1. Here, this is the reachable set, which is the collection of all these points. Again, it's same, right? What about this guy? This reachable set looks like this guy. Well, this is the x naught. So it's accessible because the reachable set has 90 interiors. X naught is in the boundary. If x naught is in the boundary, then it's not small time locally controllable, right? It's not small time locally controllable. What about controllability? It is. Here it is. The reachable set from the origin is the entire manifold, so this is controllable. So sometimes you have controllability, but not small time locally. So small time local controllability is actually stronger notion than controllability. Controllability is what? Eventually I'll go there. But small time locally controllable is that, okay, you will do it in a small time. You will do it not because the nature of the manifold or the nature of some vector field that will eventually wrap around. You will do it because you really have the capability to do it, to go around, locally around the point. Okay? Is it clear enough?
But why is it not STLC? I don't see it. If the manifold is S1 times R.
Yeah, because I cannot go backward from this red point. I cannot go backward in theta, locally. If I want to go to negative theta, I have to wait long time to come by the natural flow.
Yes, Professor, but the first example you gave us in differential geometry, the sidecar or the four-wheel car, it seems like it's not small time controllable.
Why?
Because I can't move sideways, but when I apply the Lie bracket, I can move in this direction.
Why not? Why it's not small time locally controllable? You can move sideways by doing this Lie bracket in a small time, whatever it is. I mean, we're not saying anything about the bounds of the control now, right? If I want to move almost pure, it's not about generating velocity sideways, right? It's about, can you go sideways? The reachable set in very small time. Well, yeah, I can do it. I will do this Lie bracket very fast and come sideways.
Okay.
But here in this example, I don't have this capability. I actually have to just wait. If I want to go to here 10 degrees, so I have to wait for this dynamics to take all the time 350 degrees. I'm doing nothing, right? So these are fundamentally different. Any question? So next time we will talk about more about controllability and sufficient conditions. Okay. So the homework next time. See you next time. Thank you.